I've been doing a lot of problems where I kind of made up the numbers so everything worked out nice and neat and clean. But now I got this problem off the internet, and I think this will be instructive because the numbers aren't so easy. It's not like, sine and cosine of 30 degrees. We're going to have to deal with 35 degrees. And just so that I can make sure that we get the same answer that they got, I'm going to use 9.8 meters per second squared as acceleration of gravity instead of 10. So let's do this problem. So let's see what's going on here. We have this inclined plane or this wedge or this ramp or whatever you want to call it, and you have a 10 kilogram mass sitting on the ramp. Then there's this massless rope or wire that goes over this pulley, and then that same wire goes and is attached to a 20 kilogram mass that's just hanging there. So what's going to happen just very intuitively? Well, here you have the whole force of gravity pulling down on this 20 kilogram mass, and then here pulling back on this, you're going to have the mass of this, and let's just assume, just to get the intuition that there's no friction, just to figure out which direction things move in, you're going to have the parallel component, the component of this object's weight that's parallel to the ramp pulling back. And so that's going to be something less than this object's weight, right? This object's weight is roughly 98 newtons, so what's pulling back on it's going to be something less, I don't know, 50 units, 60 newtons, we'll figure that out. But clearly, the weight pulling straight down on this object is greater than the force pulling back parallel to the ramp on this object. So the whole system will move to the right. And so the whole system will move to the right, we know that the force of friction is going to act backwards because it always acts against you. So let's do the problem. Let's do the math now that we have the intuition of what's going to happen. And of course, this object will fall, or it will accelerate downwards slower than it would have if it wasn't attached to this whole mechanism, right? Because this will be pulling back on it a little bit. So the problem tells us that the coefficient of friction between this mass and the ramp is 0.2. It's 0.2. So we can just go into our mode, because this is the hard one, just to figure out what happens with this object, because it has friction, it's on an incline. So let's see what happens. So first we know that there's the force of gravity pulling straight down on it. Right? That's the force of gravity. And then we'll have, and I know I always change words because I actually don't know the correct well, it seems like almost everyone uses different conventions for these, but you have the perpendicular component of gravity, right? Which is that force. And then you have the parallel component of gravity. Let me switch colors. The parallel component of gravity, which is that force. This force. And of course, we have to figure out the perpendicular component, which is the same in magnitude to the normal force. And that helps us figure out what the force of friction is. And then we use the parallel force to just figure out what the force is that, how much of gravity is pulling parallel to the ramp backwards. So let's do that. So first of all, what's the weight of the object? Well, it's 10 kilograms, and the acceleration of gravity is 9.8 meters per second squared. So 9.8 times 10 is 98 newtons. 98 newtons. And we've learned from previous videos that if this angle is 35 degrees, this angle is 35 degrees as well, so I won't reprove it here. I know you can't read the 35 I just wrote. And that should hopefully start making intuitive sense to you. So if this is 35 degrees and this is 98, what is this side equal to? The side that's perpendicular to the surface of the ramp. Well, adjacent over hypotenuse is equal to cosine. So this side is equal to 98. So this side is equal to 98 cosine of 35 degrees. 98 cosine of 35 degrees. And I do not know what the cosine of 35 degrees is, so I will use my calculator. So the cosine of 35 degrees is roughly 0.82, and then I multiply that times 98 times 98. That equals roughly 80. So this equals 80 newtons. This vector right here. So there's 80 newtons. The part of gravity, of the component of gravity that is pulling perpendicularly down to the surface of this ramp is 80 newtons. And of course, the normal force, that's the force that the weight is kind of pushing into the ramp, and the normal force is just the equal and opposite force that the ramp is pushing into the weight. right? That keeps the weight from falling into the ramp. And so that's also going to be 80 newtons. So the normal force is also 80 newtons. And the only reason why I point that out is just because I wanted to start referring to the normal force just because I didn't have a variable here. But anyway, so you could say that the force of friction now, so the force of friction, which we already determined is going backwards, because we determined that the whole system will move to the right. And we just figured that out just by looking at the relative magnitudes of the masses. So the force of friction is equal to the coefficient of friction, 0.2, times, you could either say times the normal force or times the force of gravity going perpendicularly down into the surface. But either way, that's going to be 80 newtons times 80 newtons. And 0.2 times 80, well, that is equal to 16 newtons. Excellent. So we figured out that the force of friction pulling back on this object is 16 newtons. And what's the component of gravity pulling back on this object, or this vector right here, going parallel to the surface? Well, we've done this a lot, and I'll call this force parallel just because I need something. The force parallel, this is the opposite side, this is the hypotenuse. Opposite over hypotenuse is equal to sine of 35 degrees. So this is equal to, we've done this a lot, so I won't go into the detail of the math, 98 sine of 35 degrees. Go back to the calculator because I have not memorized the sine of 35 degrees. 35 sine is about 0.57 times 98 is equal to 56. So the force parallel is equal to 56 newtons. So there's two forces pulling back on this object, right? One is 56 newtons, and that's just the component of gravity parallel to the surface. And then you have the force of friction pulling back. And of course, the force of friction is always acting against you. So the total forces pulling back on this object, if you add these two, 56 plus 16 is 72 newtons. So there's 72 newtons of force essentially trying to pull this whole system back, right? You can almost view it, there's 72 newtons of force pulling up on this object too, right? That's what's pulling this whole system back. And now what's pulling this whole system to the right? Well, it's the weight of this object. And what is the weight of this object? Well, the weight of that object is 20 times 9.8 meters per second squared. So the downward force, the force of gravity, so that's this force. Let me do a different color because it's getting messy. That downward force is just 20 times 9.8, so it's 196 newtons. So you have 196 newtons pulling this way, so it's also pulling up here. So the net force on the system, think about it this way: you have 196 newtons that wants to go roughly in that direction, and then you have 72 newtons that wants to go roughly in that direction. And I know maybe it makes it a little confusing with this pulley and all of that, but hopefully that makes some intuition of, there's two directions it can go to. It can go into the up and down direction, or the up into the left direction. So what is the net? What is the net of these two? Well, what's 196 minus 72? So the force net, so the net force trying to go in that direction, the net force is 196 minus the force of friction minus this parallel force, which is 72. The combined force of friction and the parallel force is 72. So it's 196 minus 72 is what? 124 newtons going in this general direction. 124 newtons. And so what is the acceleration of the system? Well, to know the acceleration of the system, we have to know the mass of the system. And what is the mass of the entire system? Is it just the 20 or is it just the 10? Well, no, it's both, because the entire system is moving. The entire thing, this entire contraption, this whole mass and a wire and the other mass, it's all being accelerated. So the total mass is 30 kilograms, 10 plus 20. So you have the force, 124, is equal to the mass, 30, times the acceleration. So the acceleration is equal to 124 over 30. And that is 124 divided by 30 is equal to 4.13, equals 4.13 meters per second squared. So this whole system will accelerate well, here it'll accelerate up and to the right, and then it'll accelerate downward at 4.13 meters per second squared, which also makes intuitive sense because essentially this mass has slowed down this object's descent, right? If this was completely unattached to this wire, it would have fallen at 9.8 meters per second squared. I'll see you in the next video.